Hello everyone. So in the last video lecture we have started our conformational isomerism, right? And in conformational isomerism as well, I have discussed various topics like van der Waals stain, torsional stain, dihedral angle, difference between dihedral angle and bond angle, and how to draw different types of projection formula. So let's continue our topic. Okay. Draw conformers of first. Okay, so in these two questions you have to draw their conformers and you have to check about their stability. Okay, so let's draw first one. For this question you can see here 1 2 3 carbons are there. Now the first question is, sir, we have to draw the conformer of this compound with respect to which carbon? Because as per the numbering, if you will see IUPAC numbering, so you will find as per IUPAC numbering it is having 1 2 3, right? So it is actually propanol. So you have to draw across C1 C2. So now you can see from C1 here it is 2 hydrogen and 1 OH. Here it is 2 hydrogen and 1 CS3. So the possible cases are, now I am drawing front carbon like this. This will be having suppose 1 OH and 2 H. Now for back carbon you are having 2 hydrogen and 1 CS3. Okay, so here you can see this front carbon having OH, 2 hydrogens, in back carbon 2 hydrogens and 1 CS3. Now this is perfect structure. Now this one is staggered form. Okay, now again if I will rotate it to 60 degrees, suppose 60 degree rotation, what I will get? Keeping front carbon as it is, if I rotate backside, so what will happen? You can see this group will move this side, this group will move this side, and this will move this side. So what will happen? If you see, this group will be just backside of this bond. So for better visualization I am drawing after this one. Okay, so it is parallel to each other, both are in front of each other. Now after this bond, so after this one H, after this one H. So this is your eclipsed form, right? Now again there is one more possibility you can observe. If I will make again 60 degree rotation, keeping front carbon as it is, what I will get? This is CS3 H. Now as you know this is also staggered form, but here the term, this will be your fully staggered, this is your partially staggered, which is also called as gauge form, right? Now again rotate it to 60 degree, same clockwise, and you will get keeping front as it is, and here you will get, this will be your CS3 H. Now this is also eclipsed form, but here you can see that was your eclipsed with partially eclipsed. Why? This OH is one of the bulky group and this CS3 is bulky group, but they are not eclipsed with one another. Here both are eclipsed with one another, so it will be your sort of fully eclipsed, right? So these are the 4 possible cases for propane vanol across C1 C2. Okay, now let's find their stability order. So here we can see in case of staggered form, these two staggered form, there is least van der Waals strain as well as torsional strain. Okay, but in case of staggered form, either this either this eclipsed form or this eclipsed form, in both the cases there is maximum torsional strain due to these two bonds parallel to each other in front and back of each other. That two electron pair of this bond and that bond repel each other to the maximum value, as well as the two groups repel each other due to van der Waals strain, right? So we can say here, in these four cases, you can say the most stable form will be, the most stable form among these will be fully staggered is most stable, then gauge form or partially staggered, then you can say partially eclipsed, then you can say fully eclipsed. Okay, here we need to remember that in case of van der Waals strain between the two groups or one atom and one group or between two atoms, as the bulkiness of the group or atom arises, then the van der Waals strain again arises, right? Okay, so this was all about propane 1-ol. So I hope it is clear. You have noted everything, each and every point. You have understood it completely. Now let's come to second one. This part is your 1, 2 across this part. So this is your C1C2. It is actually ethane 1,2-diol, right? Ethane 1,2-diol. Okay, so we have to draw conformer of ethane 1,2-diol across C1C2 carbon atom. Suppose I am telling from this carbon, front carbon, 2 hydrogen and 1 OH. Okay, 1 OH is here, H, H. From back side 2 H and 1 OH. I can draw OH, H, H. This is your fully staggered form. As we see, both OH are, one is from front side upward and back side downward. Okay, now again, if I draw its partially staggered form, this OH will be here, H, 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 H. Now if I have to draw eclipsed form, this will be your eclipsed form. So there are two cases of eclipse. What? In one case you will have fully eclipsed. In that case you can have this OH, and in another case, in case of partial eclipsed, you can say it as this will be your OH. Okay, I am directly drawing. I am not explaining you in terms of if you rotate 60 degree then again rotate 60 degree. I am just drawing all the four cases here, right? Now in these four cases you have to understand there are some special cases where partially staggered or gauge form becomes more stable relative with fully staggered form. The main reason behind such cases are hydrogen bonding. Here you can see this oxygen is having lone pair which is having attraction forces with this oxygen is having lone pair which is having attraction forces with this hydrogen. Okay, so here you can see due to this chelate ring formation, intramolecular hydrogen bonding, gauge form, gauge, or you can say partially staggered. This is your partially eclipsed, this is your fully eclipsed, this is your fully staggered, or this is also called anti because these two groups are anti to each other, right? So in such cases gauge form becomes more stable. Reason, intramolecular hydrogen bonding. Okay, so in this case you can say the order of stability will be partially staggered is more stable. Now you may have the question, sir, in case of this fully eclipsed form there is also hydrogen bonding. Yes, that is absolutely correct. In case of fully eclipsed form we do have good sort of hydrogen bonding, but in this case you have this eclipse bond, right? eclipsing part. So these two are having van der Waals stain, as well as you have good amount of torsional stain due to these bonds. So torsional stain is also there. So that's why the most stable form will be your gauge form. Okay, after that you can say fully staggered form, then you can say in these two cases partially eclipsed, then after your fully eclipsed, because the stain part is also available in this question, right? So I think you have understood this entire part and how to draw all four types of conformers and intramolecular hydrogen bonding. Now let's take some particular examples. So here you are given these two cases and you have to draw the most stable conformers, right? So first of all, you need to understand in this one, if I will number it 1, 2, 3, 4, 5, as per IPSC naming, it is 2-methyl pentane. Here I have to draw with respect to C2, C3. Okay. So from C3 you can see 2 hydrogen as well as 1 ethyl group is there. From C2 there are 2 methyl groups and 1 hydrogen. As we know, the eclipsed form will be least stable, so we don't need to draw the eclipsed form. Okay, either it is partially eclipsed or fully eclipsed. So I will just draw the two cases of staggered form. Then we will compare which is more stable, and hence that will be your answer. So in case of this one, here from this C3 you are having ethyl group. So this is C2H5, hydrogen, hydrogen. From C2, 2 methyl and 1 hydrogen. So if I will make 1 methyl here, 1 methyl here and 1 methyl here. Okay, so this is one possibility. And another possibility is, this is C2H5. Both methyls are nearby C2H5, H. You can see here, this is having your, suppose I will say this is your front carbon. So front carbon ethyl HH, front, and this is your back, ethyl HH. Okay. Now from back, 2 methyl and 1 H, 2 methyl 1 H. This is perfect. Again here, ethyl HH, 2 methyl H. Comparing these two structures, what you see is, in this case, it is staggered, no doubt. So there is least amount of torsional stain, lesser van der Waals stain. Between these two groups, you are having van der Waals stain. Okay, they are in 60 degree to each other. Dihedral angle here is 60 degree. But when you make this structure, and how will this structure arise from this structure? If you rotate this structure 120 degree anti-clockwise, 120 degree anti-clockwise, okay, so you will get this structure. This will come this side, that will go this side, and this will come here. So you will get this structure. Here, this C2H5 is having van der Waals stain with both the methyls. So you can say this structure is more stable. Okay, so 1 and 2, you can say first is more stable than second. So your answer will be first structure. This is your answer, most stable conformer of 2-methyl pentane. Clear? Now come to second one, this one. Here you can see, if I will make numbering 1, 2, 3, 4, 5, 6, it is 6 carbon chain, 2 methyls, 3 1 methyl, 4 1 methyl, 5 2 methyls. So you are having actually 2 2 3 4 5 hexamethyl hexane, and you have asked to draw across C3 C4. Okay, across C3 C4. Now you have to see, suppose your fourth, you know in 3 and 4 both cases these are having a hydrogen, both are having methyl, and both are having this tertiary butyl group. Okay, so these two tertiary butyl group, as we know, we need not to draw eclipsed form. Now we have to draw staggered form. Again, in staggered form, you can see this bulky group from C4 and this bulky group from C4. If I draw these two anti to each other, both are just anti from each other, then that will be the best possible case, because these two are the most bulky group here. Again, you are having hydrogen in C3 C4 and methyl in C3 C4. If I'll again make this two methyl group anti to each other, then both hydrogen will also be anti to each other. That will be the best suitable case. So in such questions, either you can draw both the cases or all 3 or 4 cases, whatever is possible, or you can first make your imagination through mind that what are the possible cases and which will be the most suitable case. So from observation, I can say the best possible case will be from front carbon. Suppose I make C3 as front carbon and this as back carbon. Okay, so here you can see from front carbon, this tertiary butyl, this is CMe3, right? CMe3. Now it is having one methyl. Now methyl is here and hydrogen is here. Okay, now backside carbon is again having methyl, so make this methyl and that methyl anti to each other. Okay, now again this tertiary butyl anti to this one and this hydrogen anti to that hydrogen. So here you can observe this CMe3 and CMe3 are anti to each other. This methyl of front and this methyl of back is anti to each other. This hydrogen of front and this hydrogen of back is anti to each other. So this is the best possible conformer and most stable form for this question. Okay, so I hope you must have noted everything, you have understood. I'll suggest keep drawing all the possible cases of this compound. Let me explain. If you rotate this to 120 degree clockwise, suppose if you rotate 120 degree clockwise, so this hydrogen will come here, this CMe3 will move here, and this methyl will come here. So that is a case where this CMe3 will be having CMe3 of backside here and methyl here. So there is a case when you have CMe3 and methyl. Okay, with respect to this CMe3, you are having methyl and CMe3 here. Again, one more staggered form will be when you have CMe3 here and hydrogen here. So two more staggered form are possible for this example, right? Methyl hydrogen or methyl CMe3 or hydrogen CMe3. Three possible staggered. The best possible and the most stable conformer is this staggered form. Okay, I think you are clear with this example. So find dipole moment in conformers. Now, one of the best question in case of conformers which has been already asked in various competition examinations including JEE examination. Draw the structures and find the dipole moment of the given conformers, right? So let's take a very easy example of butane, or you can say take example of ethane. Let's first take an example of ethane, CH3. You know you are having two conformations. One is your staggered form and another is your eclipsed form, right? Now suppose if you take a solution of ethane in a container, so if this ethane forms various conformers and only these two forms of conformers are possible, so we can say that the solution must be having some amount of staggered form and the remaining amount of eclipsed form. Here we don't know what is the amount of staggered and what is the amount of eclipsed, but I can say that let the mole fraction of staggered form in the solution be x1. x1 is mole fraction of staggered form in solution. Okay, now here you can say x2 as mole fraction of eclipsed in solution, right? So you are having x1 mole fraction of this staggered and x2 mole fraction of eclipsed. Now suppose you are having dipole moment of staggered mu1 and here the dipole moment is mu2. So according to the calculation part, net dipole moment mu net is given by the formula mu1 x1 plus mu2 x2. Okay, so note it down, this formula. If you are having any compound or a solution in which one compound is present, so as per this example, ethane was given. Ethane solution is having staggered form as well as eclipsed form. This is having mole fraction x1 with dipole moment mu1. This is having dipole moment mu2 and mole fraction x2, right? So if suppose you are given net dipole moment of the compound, so how will you found? Any of the following four entities can be asked. You may be given mu net or you may be asked mu net. In that cases, you are having 5 variables: mu net, mu1, mu2, x1 and x2. Out of these 4 variables, you must be given the 4 part and 1 part will be asked. Now in such cases what happens? Sometimes it is said that only stable forms will be available in the solution. So in that case you can understand that there will be availability of only staggered form, there is no eclipsed form. But in case if you are told that all the possible cases are present, then you have to understand that in which conformer there is net dipole moment 0. Just like in case of this staggered form, you can see the dipole moment of this form must be 0. Why? From front you are having hydrogen this side, from back hydrogen anti to each other, so all the anti portions hydrogen cancel out the dipole. So in this staggered form is having dipole moment 0. So you can understand mu1 is 0, x1 may be any amount, mu1 x1 must be 0. So net dipole moment of ethane must be due to mu2 x2 here in this example. I think you are clear with this form, right? So let's take one example of calculation of dipole moment using this formula. Draw stable conformers of P, CH2, CH2, P. P is equal to any group. Now you have to understand, you have to take any hydrocarbon part, right? That P must be any alkyl group. You won't have to make exceptional cases like OH-OH group or OH-NH2 group where there are some abnormalities due to hydrogen bonding. So in this case, find the dipole moment of gauge form if mu solution is given as 2d by and mole fraction of antiform equals to 0.8. Okay, so now let's understand this question. First of all, we need to draw the conformer. Now, as the question has already mentioned that you have to consider only stable conformers of this, means we have to ignore eclipsed form, right? So in such a case, suppose this P, any group, anti to each other, H, 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 H. Now next, now these are the two possible cases of conformers which are stable form. This is your partially staggered or gauge form, and this is your anti form or fully staggered. So among the two cases, you can say mu net equals to mu anti mole fraction anti plus mu gauge mole fraction gauge, right? Mu net is already given as mu of solution equals to 2 d by, that is equals to mu a anti. Now you can see from the structure that this anti form is having dipole moment 0. So mu a is actually 0. So 0 into xa will be 0 plus mu gauge that you need to find, and x gauge mole fraction of gauge form. Now you have been given in the question mole fraction of anti form 0.8. Now we can understand if the two conformers gauge form and anti form is present in the solution, then the total mole fraction will be equal to 1. So you can say mole fraction gauge plus mole fraction anti equals to 1. So mole fraction of gauge equals to 1 minus mole fraction of anti form. So here mole fraction of anti form is 0.8. So mole fraction of gauge form will be 0.2 because 1 minus 0.8 is 0.2. So here you can say mu gauge equals to 2 upon 0.2, that is equals to 20 by 2, that is 10. This is your answer. Okay, so from the given data you can say that the dipole moment of this gauge form will be your 10 dBi. Okay, in unit, for dipole moment you have been given dBi unit, so it is 10 D. Answer clear? Okay, so let's now continue with our next topic. Conformational energy barrier. Now what is this? As we know that one conformer is easily converted or rotated into another conformer. How? Due to single bond free rotation, right? So but there must be, from interchanging one form to another form, there may be energy variations. So this is studied in conformational energy barrier. Let's take the easiest example again, ethane. Okay, as we know, two conformers are possible. From these two conformers, you can say this is your staggered, this is your eclipsed. From these two cases, we can understand if we rotate 60 degree, we will get this conformer, right? So let's draw potential energy versus conformation. Now here, observing this structure 1 and 2, you can say staggered is more stable. 1 is more stable than 2. This is the order of stability. And as we know, potential energy is inversely proportional to stability, right? So more stable will be having lower potential energy. This is your potential energy curve. Okay. So suppose this is your staggered form. Okay. Now this energy is supplied. Again, this is your structure number 1, staggered form. Now when you apply this much amount of energy, then staggered will be converted into eclipsed form. Again, On releasing this much amount of energy, it is again converted to this form. Okay, so this is your rotational energy barrier from 1 to 2. Okay, so this is your staggered, this is your eclipsed, and this is your again staggered. So here you can say that interconversion energy barrier or conformational energy barrier. I am not talking about the total energy or the energy possessed by structure 1 or 2. I am just talking about the energy between this interchange or interconversion. So this is the energy, right? So such graphs are drawn. In case of ethane, if I will say the data, as per correct data, it is approximately 12 kilojoule per mole. The energy conversion rotational barrier for ethane is 12 kilojoule per mole, right? Clear? So again, if I will take another case of propane. So in case of propane, you can understand propane CH3, CH2, CH3 across this carbon. You can draw this carbon is having CH3. Suppose this is front carbon and this is back carbon, CH3 H, and back one is having 3 hydrogen, right? Another case is CH3 H. Only these two possible conformers are possible. Again, this is your staggered form and this is your eclipsed form. If I will draw the rotational energy barrier for this conformation, then it will be again like this. But here, if I will compare as ethane and propane, then in case of ethane, there was hydrogen, right? But here there is CH3 and hydrogen. So if I'll consider the van der Waals stain or if I'll consider the torsional stain, in both the cases, both must be increased here in case of propane as compared to ethane. Why? Because the groups are bulky here. Hydrogen is replaced by CH3. Okay, so we can understand if this is 1, this is 1 and this is 2, the energy, potential energy versus this is your staggered, this is your staggered and this is your eclipsed. This energy must be higher. So here it is approximately 13.8 kilojoule per mole. Clear? Okay, let's come to the most important part of this conformational energy barrier. That part is actually your butane. Let's see the complete structure of butane once again, drawing all the conformations starting from fully eclipsed form, means starting from dihedral angle 0. If we keeps on rotating one by one to form all the conformers till 180 degree and then 360 degree, drawing all the important conformations, what can be the energy graph? So first of all, this is your CH3, okay. This is H. You can see this front carbon is having CH3HH. Then your back carbon is also having CH3HH, means it is already butane, and you are drawing across C2, C3 of butane, right? So you are drawing conformer of butane across C2, C3. Now this is your fully eclipsed form, okay. Rotate it by 60 degree clockwise. I'll be rotating by clockwise only, okay. So what you will get, keeping front carbon as it is, you will get this form. This is your partially staggered or gauge form. Again rotating it 60 degree, I will be getting keeping front part as it is. Now this CH3 or Me, that is same thing, right? Here your CH3 H. Now this is your eclipsed, but here both CH3 are parallel to each other, in front of each other. So this was fully eclipsed. Here it is partially eclipsed. Now again rotating it 60 degree clockwise, what you will get? CH3 H, okay. Now again, now what is this? This is your fully staggered. Why? These two CH3 are anti to each other. Now again rotate it by 60 degree clockwise. What you will get? CH3 H H. This will come this side and this side. This CH3 will be here. H H. Again I am rotating it by 60 degree clockwise, and what I will be getting? Keeping front part as it is, this CH3 will come this side. Okay. Now you can see this is again your very similar to this partially staggered form, right? So if I'll see, and again if I rotate it by 60 degree clockwise, what I will get? CH3 H H. This will come this side. CH3 H H. This is your fully eclipsed. You can see this is your structure number 1. Okay, it was your fully eclipsed, rotating 60 degree. Your structure number 2, again 60 degree. 3, as compared to first structure, this is 60 degree rotation, this is 120 degree, this is 180 degree rotation. This is again your 180 plus 60, 240 degree rotation. Again, this is your 300 degree rotation with respect to first one. And finally, this 7th structure comes when you rotate 360 degree to the back carbon, keeping the front carbon as it is. Front carbon is as it is. If you rotate back carbon 360 degree, you will get this structure. First and 7th is having similar fully eclipsed, so it must be having similar energy. You can say stability order, if I will say, so the most stable form you will be fully staggered, right? So you can say here fully staggered form is fourth one, and again fully staggered is your no one. Then partially staggered, so your second one, and again sixth one. So you can say second and sixth must be having same stability. Then partially eclipsed, so it is your partially eclipsed third one, and your partially eclipsed, this one will be your partially eclipsed fifth one. So partially eclipsed fifth one, and last come to first equals to 7, because this is your fully staggered or anti form. This comes your partially staggered or gauge form. This comes your partially eclipsed, and this comes your fully eclipsed. Okay, so you can see this entire structure and everything starting from 0 degree, 1 2 3 4 5 6 7 up to 360 degree rotation. Okay, so structure 1 and 3 from 120 degree, similarly 1 and 7 from 360 degree. So this is the order of their stability. Again, if stability is more, potential energy will be less. So let's draw the potential energy diagram, and you can see what is the conformational rotational energy barrier in case of butane across C2, C3. Okay, so first of all you draw this complete structure, then I will see the energy form. Okay, so here you can see this part first and 7th are almost similar, right? So I'm just drawing it here. You can see properly. I'll draw it a little smaller. So here you can understand the first one. Suppose this is having potential energy this much, right? From starting from here. So it will first make partially staggered. So this is your partially staggered form. Okay, now second to third, that will be your eclipsed, but it is not fully eclipsed, partially eclipsed. So energy will rise. Again, what you will get on rotation? Fully staggered. So here you can see that you come across fully staggered. Now again, if you will see from fully staggered to partially eclipsed, means this same again, right? Partially eclipsed towards partially eclipsed to partially staggered, again this one partially staggered. Now come to this part. So in this structure, if I'll observe each and every point starting from fully eclipsed to this one was your second partially staggered, to third that was your partially eclipsed, then your this was fully staggered, again to partially eclipsed, again to partially staggered, and finally this again fully eclipsed. So this was your 0 degree, on rotating 60 degree, on rotating 120 degree with respect to 0 degree, then 180 degree, then 240 degree. Okay, this again 300 degree, and finally this was your 360 degree. So starting from first one, so here you can see this entire structure of butane conformational isomer, all the important isomers and their energy profile diagram. This is your potential energy and these are all your conformers, right? So let's see entire part. Starting from fully eclipsed, it is having maximum energy, towards your partially staggered, towards your partially eclipsed, then your fully staggered. Okay, so now let's see as per the data. Suppose you are asked numerical value type question, or suppose you are given with single correct type question, but in that you have been asked a data based problem. So we need to remember some values. Okay, so with respect to fully staggered, if I will see the energy barrier with respect to fully staggered and fully eclipsed. So this part, fully eclipsed to fully staggered, this energy barrier is approximately 19 kilojoule per mole. You have to remember fully eclipsed to fully staggered 19 kilojoule per mole, because they are having far apart in stability, fully staggered versus fully eclipsed. Okay, then if I will see fully staggered versus partially eclipsed, this energy barrier is approximately 16 kilojoule per mole. So you can see this is fully staggered and this is your partially eclipsed. Obviously they are having big difference. So this is 16 kilojoule per mole. Okay, now if I will see fully staggered versus partially staggered, so they are just a bit apart. So you can say this energy gap will be little lesser. It is nearly equal to 3.8 kilojoule per mole. Okay, so again I am repeating, from most stable to least stable the energy gap is 19 kilojoule per mole, from most stable to partially eclipsed 16 kilojoule per mole, and third one 3.8 kilojoule per mole. Okay, so I hope you must have drawn this entire diagram and you can see, note it down properly, and you have to remember this entire part in proper way. Okay, so we can see here we studied about conformational energy barrier, we studied about important conformations, how to draw different conformations, in which cases gauge is dominating as compared to fully staggered. We understood about how to calculate dipole moment of different conformers. So now let's take a few important examples. Okay, a few different cases, special cases. First one is draw most stable conformers in pH values. First, pH very less than 7. Second, pH very high than 7. So you can see we have been given two cases. If pH is very less than 7, now as we know, if pH is much less than 7, the solution must be acidic, and if pH is very higher than 7, it must be basic, right? Now the given compound is actually 1 2 3 4. It is your butane 1,4-dioic acid, or simply you can say butane dioic acid. So in this we have to draw conformer across C2C3. Okay. Now if I will say the solution is acidic, then it must be existing in this form only. So the most stable form will be obviously think. So most of the person must be thinking, I think students, you must be thinking that this will be the most stable form because these two are anti to each other, but here you are wrong. Why? Because it is having OH, it is again having OH, so the most stable form will not be fully staggered, rather it will be partially staggered, or you can say here the most stable form in acidic medium will be this one, right? Why this one? Because it is gauge, and here we can observe intramolecular hydrogen bonding. Okay, so this is the case of first, right? pH very less than 7, solution is acidic, so it will exist in this form. In this case there will be intramolecular hydrogen bonding. But if the solution is basic, we can understand it will exist pH greater than 7, it will exist as CH2 CH2 COO minus COO minus. So the most stable form will be here anti form, obviously H H H H, and this must be existing like this form actually. Okay, or you can say here COH COH, right? So I think this was one of the most important case you have understood. So let's take last example of this session, in which cases gauge form is dominating. In which cases gauge form is dominating? First, fluorine, OH, OH, NH2, OH, fourth, this OH, COOH, okay, COOH. Fifth, OHCl. 6, OH, and here you are having CS3. 7, CS3 NH2. NH3 plus, and this is your methyl. Now you have to understand in the given cases which is having gauge form or partially staggered form as the most dominating part. You can see one by one. If I draw across this, you have to draw across C carbon-carbon bond. Okay, so in first case, if I'll observe this fluorine and this hydrogen of OH must be having intramolecular H bonding, so gauge will be dominating. In case of NH2 and OH, obviously here gauge form is dominating. Here again this aldehyde part is having oxygen, which is delta negative part, and H, here it is having intramolecular H bonding, so this is also a case. COH and OH, again gauge form. Cl, yes, this is a very special case. You have to understand, this question gives you a big clarity of electronegativity, hydrogen bonding, which comes under chemical bonding chapter, as well as hydrocarbon chapter, as well as alcohol phenol ether chapter, as well as haloalkane and haloarene chapter. Understand, here chlorine is having good amount of intramolecular hydrogen bonding, so here gauge form will be dominating. Here this CH3, the hydrogen which is attached with more electronegative elements like oxygen, fluorine or nitrogen will only undergo hydrogen bonding. Again, hydrogen bonding can be done by most electronegative elements like fluorine, oxygen, nitrogen, in some special cases chlorine. Okay, so here you can see this carbon cannot form hydrogen bonding. Hydrogen attached with carbon also cannot form hydrogen bonding. So here in this case you can say gauge form is not dominating. Again this CH3 and NH2, gauge form is not dominating. Again this CH3 and NH3 plus, gauge form is not dominating. So you can see in case of 1 2 3 4 5 6 7 8, among these 8 only 5 cases where gauge form is dominating. Okay, so I think it is clear to you. I have explained everything. This was one of the most important part of conformers. I have explained about butane, various energy diagram for butane, potential energy curve, then about propane, then ethane and everything. So we'll continue our topic in next lecture. Okay.